Hello everyone, you are welcome to session 5 in part 1 of linear algebra from the course of deep learning and applications. Today we continue the previous sessions which is mainly based on general review and fast review for linear algebra, and mainly we focus on the topics which are applied in deep learning and in machine learning in general. Okay, we continue today. Actually, we will talk more about the decomposition of matrix, and mainly we will discuss the singular value decomposition, which is one of the most important decomposition eigen-decomposition algorithms. And we will see the difference between singular value decomposition and the diagonalization that we saw in session 4. Okay. Yes, so before we continue, let us talk a little bit about the transpose of matrices. We already saw what is the meaning of transpose, and we said that we swap between rows and the columns. And if we have a matrix C, matrix C equal to, for example, matrix A times matrix P. So to have legal multiplication of matrices, we will assume that this matrix A is n by m, and matrix B must have m rows, but it can be the columns like k, and of course the resultant matrix will be n by k. Okay, and if you check the transpose, so C transpose actually will be k by n, and C transpose equal to A times P all transpose, and this will be B transpose times A transpose. So this is important to see in this matrix operations. Okay, and remember that if K does not equal to like m, if K does not equal to m, then or does not equal to n actually, then B or A times B does not equal to B times A. This is in general. This is not valid. This is not valid. You cannot swap or exchange the multiplication in matrix in general, of course. Okay. However, of course, it can be possible in some times. For example, if you have matrix A multiplied, it is transpose version. Okay. So that this matrix A, if it is n by m, then A transpose will be m by n. So the result will be the resultant matrix, for example, B, will be like n by n. But if you swap it, if you multiply A transpose by A, okay, which will be m by n times n by m, so the result will be, for example, matrix C will be m by m. Okay, so this is in general that it is in the multiplications if they are not in the same dimension. Okay, and what else? Now before we go to the singular value decomposition, let us try to solve some like non-square system of system of linear equations. What I mean, assume that you have, let us start with a new slide. Okay, assume that you have these equations. Now we have x1 plus x2, let's say, is equal to 1, and x1 minus x2 is equal to, let's say, 2. Okay, and 2x1 plus 3x2, let's say, equal to 5. Okay, now we have 3 equations into 2 unknowns. Okay, if we take only 2 equations into 2 unknowns, and if there is no equation, just a linear dependent of the other, as we saw before, it can be solved easily. And if the matrix is non-singular, because we don't have or it has full rank, then we will have single solution for that. as we know. But in this case, actually we have three equations, and all of them, they are independent, and we want to find this solution. Of course, in this case, there is no single solution, or there is no solution to achieve all or to satisfy all these equations. We don't have x1 and x2 which can satisfy all these equations. What we should do, we can in this case we can make a slight change to, we say that x1 plus x2 minus 1 equal to, this should be 0, but since we cannot achieve all of them, I will put here like error 1, okay, and x1 minus x2 minus 2 equal to error 2, and 2x1 plus 3x2 minus 5 equal to error 3. Okay, the problem now, it has been changed. Instead of finding the exact solution, so now I am interested to find what is the optimum x1 and optimum x2, which makes this error very small. Okay, of course this will depend on the criteria, on what criteria that we need to minimize the error. If we take the L2 norm, or the summation of the square of errors, then the total error, it can be achieved like or it can equal error 1 square, okay, plus error 2 square. Sometimes we can put absolute value in case that that those values can be complex, but here we deal with just with real numbers, so it is enough to write just square plus e3 square. Okay, in general, if you have any number of equations, you can say that the total error, the total square error, is the summation from I equal to 1 up to n. If we have n equations, then ei square, or you can put either the absolute value of er square, or just put ei square. Okay, so this is actually the total square error. Okay, and now we try to find what is x1 and x2 which will minimize this error, minimize the total error square. Okay, and this can be done in a relatively simple way, as we will see. So to make the analysis general, so I will assume that just we have ax equal to b. We have this equation ax equal to b, where a is a matrix. Let's say that we have maybe m by n, okay, which means that in this formulation we will have n unknowns, okay, but we have m equations. Okay, so we have n unknowns and m equations. So because m is the number of rows, and here we assume that m is greater than n, so we have more equations than unknowns. Okay, so it is m by n, x will be n by 1, okay, and of course b will be m by 1. Now, what is the optimum x which minimize the error? So now the error, it can be represented as the error e, error vector e1, e2, e3. It will be also m by 1. This error will be like ax minus p, ax minus p. So this is vector. This vector consists of like e1, e2 till e, because we as we said that we have m equations, so it will be em. Okay, as I said in the beginning, that we need to find this equation, that the error of summation of ei square from I equal to 1. Here we have m equations up to m. Okay, and actually the summation, this summation could be achieved simply by multiplication of the transpose of e times e. So it will be like this error will be like e transpose times e. Of course, this is e vector times e. To explain why, okay, let me here explain what, from where this came. Assume that e equal to e1 E2, and E3. This is the error vector E. Okay, this is a little bit bold to have that it is vector. Okay, now E transpose will be this way. So E transpose will be, just we change it from column vector to row vector, it will be E1, E2, E3. Then times, this is E transpose times E times E1, E2, E3. If you multiply this together, so E1 times E1 is E1 square, E2 times E2 is E2 plus, of course, E2 square, and E3 times E3 is plus E3 square. So it is simply like that. So the multiplication, this multiplication, the transpose of a vector times the vector, if the vector itself, it was column vector, then it will generate the summation of the elements of this vector square. And this is what we have done here. So it is E transpose times E in this way. It means that the error will be like A times X minus P transpose, okay, times AX minus P. Remember here that A is a matrix with M by N, X is a vector with N by 1, and B is a vector with M by 1 element. Okay. What is our objective? What our objective is to find the optimum X which minimize this error. So we are looking to minimize this error. Okay. Yes. Of course, it can be done directly from this form, but to make you familiar how to deal with equations of matrices and vectors, I will do them like in step by step and in the long way, because the purpose here to understand what we are doing. Okay. So now, because we take the transpose, as I said in the beginning, remember that A times B transpose equal to B transpose A transpose. This is what we are doing here. So we have here A times X, but here we have a transpose. We can distribute the transpose inside. So this will be X transpose A transpose minus B transpose. So now we convert the transpose to be inside this equation. And times AX minus P. Of course, we can make the multiplication, so one by one. So I will multiply this the first term with the first term, so it will be X transpose A transpose. Be careful with the order when you multiply vectors and matrices. So X transpose A transpose times A times X. This is the first element. For the second element, minus B transpose times A times X. Okay, minus X transpose A transpose B minus X transpose A transpose times B. Okay, and finally plus B transpose times B. This is the error E. Okay, and of course we can come later about the finding the extreme values, or either minimization or maximization. Usually the differentiation of this equation should be 0 at the minimum point, or of course it can be also at the maximum. However, this equation actually is convex and it has only one minimum point, so that we can differentiate this with respect to with respect to the vector X. Remember, this total error is a scalar. This is scalar, which means that it is 1 by 1, and now we need to differentiate this scalar with respect to X vector, with X vector. Okay. Now this differentiation will lead to this value. Okay, if maybe to make things that you understand what we are doing here, I will change the color and I will show. Oh, let me first just remove to have more space, so you know that what we are doing. Yes. Okay. Yes. Actually, if we have like a general equation, for example, X vector times any general vector, for example, B times X, and you want to differentiate this one with respect with of course this is transpose with respect with X. Okay, this result, this will have B x plus B transpose x. Okay, so now if you have this the differentiation of x transpose times B times x, this differentiation will be B times x plus B transpose times x. Okay, and also this is from matrix calculus or calculus of matrices. So and also the differentiation of let's say for any matrix P times x, the result will be B transpose. Okay, and if you want to differentiate let's say the reverse, so it is x transpose times B. Okay, so the result will be B. This is general from the calculus of matrices. Okay, now we will use these concepts here. So the first thing that we have x transpose times A transpose times A. So you can see that A transpose times A is like B. So that x transpose, and here we have x. What we said, it will be like A transpose times A times x plus A transpose times A all transpose times x, but A transpose times A all transpose will be the same. Actually, it is the same. So this means that the first differentiation, it will be like 2A transpose times A times x. This will be the result of the first term differentiation. And the same will be done for here. So minus, we differentiate B transpose times A, as we can see here. Assume that B transpose times A, it is like B. So the differentiation of Bx is equal to B transpose. So you take the transpose for this one, so it becomes like minus A transpose times B. And this one is like this one, x transpose B is equal to B, the differentiation. So it will be like minus A transpose B. And the differentiation of B transpose times B is equal to 0 because it is not function in x. Because we're taking the differentiation with respect to vector x. And this should be 0. Okay? This means that 2A transpose times A times x minus 2A transpose times B equal to 0. Now we can cancel B from each side, and we can see here that the result, that this is the x star is the optimum x. So the optimum x here, it is A transpose times A times x optimum equal to A transpose times B. Okay, and then x optimum, the optimum x value is equal to, you can take the inverse of this one, so it becomes A transpose times A inverse times A transpose times B, times A transpose times B. This also one of the most important equations in linear algebra. Okay, because with this equation we can find the optimum value of x, which minimize the mean square error of the equations when we don't have square matrix A. Okay, and okay, let me clean this part to write few remarks here. Okay. Okay. So let me write those remarks here. So now, in general, if we have A times x equal to B, this is in general, and we have n as a square matrix. For example, assume that A is m by m, and this is m by 1, and A is full rank. So rank of A equal to m, and the determinant of A does not equal to 0, which means that it is non-singular equation. Then of course the optimum x in this case is equal to A inverse times B. This is the general case. when we have like square or the number of equations is the same as the number of unknowns, and we don't have any redundancy, or we don't have linear dependence between equations. Okay, now if in this form it gives us another representation of the matrix A inverse if the matrix is not square. If the matrix is not square, okay, so if the matrix is not square, then the optimum value X is equal to A transpose times A inverse times A transpose times B. Okay, so look to this part. Actually, this part is equivalent to the A inverse part. This part is equivalent to the A inverse part, for this reason that this part is called like pseudo inverse. Sometimes it is referred like A plus, which means that it is equivalent to the inverse of A, but in case that either A is singular, or if A is non-square matrix. If A is a non-square matrix, in that case we can apply this equation, and mainly when the number of equations is larger than the number of unknowns, or in other words the number of rows is more than the number of columns. There is simple modification if the reverse we have. If we have the number of unknowns more than the number of equations, actually in that case we should have like infinity number of solutions, because we have redundancy. However, we still can find what is the optimum X in which is optimum under the criteria of the mean square error. Okay, and now this is this representation. If one of you asked me why we have the inverse here, actually because we have the inverse here. A transpose times A is a square matrix, even if A is not square matrix. For example, we said that A is M by N, but when you take the transpose, it becomes A transpose is N by M times A. A is itself is M by N, so the result will be like N by N equations. So A transpose times A is N by N equations, and in that case it should have an inverse. The question now, is it necessary that always it will have inverse? Actually not, or no, because let me explain this a little bit. Sometimes even it has inverse, this A transpose times A, but it is quite common that it can be like ill-conditioned matrix, and when it is ill-conditioned, then the inverse of this matrix will have very large like numerical errors. And in that case, this could be like modified little bit, or this equation can be modified a little bit in order to find the solution. And one option is that we can say that A plus, it can be represented as the limit when some real number alpha goes to 0, okay, of A transpose times A plus alpha times the identity matrix, which should be the same dimension of A transpose times A, which is here is N by N, okay, and then we take the inverse times A transpose. I mean this part, which is A plus, it could be represented in this way. So if A transpose times A is well conditioned, then alpha, we can put alpha equal to 0, and in that case we don't have large numerical errors. But if in case that A transpose times A, it has large condition number, that by the way the condition number is the largest eigenvalue of this divided by the smallest eigenvalue. When we take the absolute value, or the absolute value of the largest eigenvalue divided by the smallest eigenvalue, when this number is very high, even if we don't have zero eigenvalues, but still it will be like ill-conditioned, and even it can be inverted, but the errors can be very large. So in that case, we can add this alpha to regular. It is sometimes called regularization factor. This alpha, in order to reduce the error. Okay, as alpha goes large, then we will have more condition number, or we will have this conditioned matrix, and this could be inverted without large errors, but in the same time we don't have numerical errors. But in that case, because alpha is large, so we are away from the original A transpose times A, which makes more errors in the construction of the matrix. If the if AT times A is ill-conditioned, okay, and we use very small alpha, or we put alpha equal to 0, then we don't have like errors due to the structure of the A multiplication or matrix multiplication, but we will have errors due to the numerical or the computations of the inverse. So usually we need to compromise between these two things. Because if alpha equal to 0, then we respect more the original form of the matrices. However, it might introduce large numerical errors, and if alpha is large, then we reduce the possibility of numerical errors, but we can be away from the original form of the matrices. Okay, so we need to compromise between these two limits. Okay, yes, now let us continue to the singular value decomposition. Okay, yes, we have already seen in the previous session that for any matrix A, that it can be eigen decomposed or factorize it into three matrices, which is X times the diagonal matrix with the eigenvalues and X inverse. Okay, so this is called eigen diagonalization, because here we have the diagonal elements of which represents the eigenvalues of the matrix A, and this will be true for square matrix A. So if we have square matrix A, then we can factorize it into this form. Actually, we have different kind of factorization in linear algebra, like QR factorization, LU factorization, which means that matrix A could be like factorized into QR or LU or whatever. So we have different kind of factorization in linear algebra, but here we try to concentrate or focus on the factorization or decomposition of a matrix, which is useful in machine learning and mainly in deep learning. So in case that we have matrix A, but this A is not square, so it is M by N. Okay, so when matrix A is M by N, so in that case, this matrix doesn't have inverse. So A inverse is not exist. But of course, as we saw before previously, that we might have the pseudo inverse A plus, and A plus actually is based on the concept that we take A transpose times A, which will be like in this case will be a square matrix. Okay, and yes, so this is the concept here about M by N matrices, that when they are not square, so we don't have the concept of inverse. We don't have actually the concept of determinant. So determinant of A is defined only for square matrices. Okay, and also the eigenvalues and eigenvectors that we saw before, it was defined for square matrices. But what the case if that we have non-square matrix like this one? And actually most of our data, if A is a matrix with data, so most of this data actually is not square. So usually, for example, if we have M is the number of rows is the data collected of patients, for example. So we have 1,000 patients. So M here is equal to 1,000, and N can be, for example, the number of attributes of those patients, which, for example, their age, gender, like their body weight or BMI, or for example blood pressure. And we might have, this is called the dimension. So the dimension N, or the attributes N, can be, let's say, a 20 number, but M can be even 1,000 sometimes. So usually we don't have square matrices or square when we talk about data. Okay, so in that case, how could we factorize this matrix A and to find what is inside or what is hidden in this data? The solution comes with the singular value decomposition. Singular value decomposition is one of the most important decomposition techniques applied in linear algebra. The idea here is said that we can factorize A like in this form. A can be equal to U, matrix U, times matrix D, okay, times matrix V transpose. Okay, now A is in the beginning I will talk about the structure of the singular value decomposition, then I will come to the explanation of the singular value decomposition. Now A is M by N, the dimension. So U is M by M, D is M by N, and V transpose is N by N. Okay, so you can see that U is square matrix with M by M, V transpose is square matrix with N by N, and D is non-square matrix with M by N. It can be square matrix if A is square matrix. Okay, and what is D? D is exactly the same as Z here or Z here. In the diagonalization, it has a diagonal element, so it is a diagonal, is a matrix with diagonal elements. And in the diagonal, with here in the diagonalization, we have eigenvalues, but in D we have what is known as singular values. And we are coming to explain what is the difference between singular values and eigenvalues. Okay, so what we have in the diagonal here is the singular values of matrix A. Okay, of matrix A. Okay, and now what this means? Okay, this U actually is nothing but is because A is M by N, so if you multiply A by A transpose, then the result will be another matrix, which let's say we call it B, and this B is M by M. Okay, is M by M. So actually U is a matrix consists of the eigenvectors of the matrix P. U is a matrix consists of the eigenvectors of matrix P. What is B? B is A times A transpose. A times A transpose, which means that B is a symmetric matrix. P is a symmetric matrix with A times A transpose, and their eigenvectors are in U. Okay, what is V transpose? V transpose is just the reverse. So if you take A transpose times A, we will have another matrix C, and this matrix C is also symmetric matrix, but its dimension is N by N. Okay, so V transpose consists of the eigenvectors of this A transpose times A, the eigenvectors of A transpose times A. Okay, there is one interesting thing here, that when you have symmetric matrix, their eigenvectors will be orthonormal. will be orthonormal. What is the meaning of orthonormal? It means that this matrix U, the inverse of matrix is the same as the transpose of the matrix. So the transpose is the same as the inverse, which means that U times U transpose equal to the identity matrix. And this actually makes the analysis much more easier than the other kind of diagonalization, because now we don't have to make any like inversion. If we need the inverse of the matrix U, you just take the transpose. This is called orthonormal matrices. This is called orthonormal matrix. And this orthonormal matrix is a special case for the eigen of a matrix of eigen vectors when the original matrix is a symmetric matrix, and this actually B is symmetric matrix and C also symmetric matrix. And okay, now what is D? D consists of that is a diagonal matrix. It is just diagonal, which means that we have only the diagonal elements, the others are zeros. Okay, and what is in the diagonal is the eigenvalues of the A times A transpose, or A transpose times A. Okay, the eigenvalues. Okay, now what is the singular value? Actually, because the eigenvalue is the square, because now we take the multiplication of A times A transpose. Okay, which means that these singular values actually which are in the diagonal is the square root of the eigenvalues of A times A transpose. Of course, we are going to explain this in more details later. Yeah, so this U sometimes is also called because it is on the left side, so it is called also the left singular value vectors of the matrix A, and this V is called sometimes that the right singular vectors of the matrix A. And as I said, that these singular values is the square root of the singular or of the eigenvalues of the matrix A times A transpose. Okay, and the number of non-zero singular values represent the rank of the matrix A. So now, because we have matrix A is M by N, so the number of non-zero singular values is always less than or equal to the minimum of M and N. Okay, because it represents the rank of this matrix, and as we know that for example, if N is less than M, then the rank will be less than or equal to N, okay, of the matrix, and this we explained in the previous sessions. So this is called the singular value decomposition. It has also many applications, and in computer packages we have always, like, it is implemented like SVD. So if you have Octave or MATLAB, if you generate any matrix A and you just write SVD of the matrix A, it will give you the matrix U, the left singular vectors of the matrix A, and it will give you also the diagonal matrix with the singular values, and also it gives you V transpose, which is the right singular or the eigenvectors of the matrix A. So, and this decomposition, singular value decomposition, is very important, and we will see some applications of the singular value decomposition in different applications, mainly in data cleaning, for example, as we see in the principal component analysis. Actually, principal component analysis is based on the singular value decomposition, as we will explain later. Okay. The last thing in this session, just 2 minutes more, I want to say that for square matrix we have the determinant A. The determinant is defined if A is square matrix, and actually the determinant is also related to the the eigen values of the matrix A. So if we have matrix A which has like eigenvalues like lambda 1, lambda 2 until lambda n, okay, then the determinant of A actually is nothing but the multiplication of those eigenvalues. So this is good to remember. And also we can define the trace of matrix A. It is called like TR of A. The trace of matrix A actually is nothing but the summation of the diagonal element. So it is the summation of the diagonal element of the matrix A. If we have matrix A like A11, A12 till A1n, and then we have A21, A22, A2n, and we have like until ANN, then the trace of matrix A is the summation of AII from I equal to 1 up to n. So it is actually the summation of the diagonal elements of matrix A. Why it is useful? Because actually the trace of A is also gives us the summation of the eigen values of the matrix A. So the summation of lambda I from I equal to 1 up to n. So actually by taking the summation of the diagonal of matrix, you can have some overview of the summation of the eigenvalues of this matrix. It has actually many other applications that we can come later. For example, how to measure the some norm of matrix A. So we have some norm like for example the Frobenius norm. It is given in this shape. This actually equal to the square root of the trace of the A times A transpose matrix. So it gives you some norm of the matrix A. We are going to talk about norms of matrices and norms of vectors in the next session. Also the trace actually of A times B is the same as the trace of B times A, if it is possible to exchange, because usually actually trace is defined for square matrices. So if A and B, both of them are square matrices which can be exchanged, so it can be done in this way. Okay, so yes, that's all. Let us stop here for this session, and then we come to the next session where we can address more points in linear algebra, which can be very important in our machine learning course or deep learning course. Thank you very much.